Hey there, and welcome. Today, we're going to be detectives. We're going to investigate the invisible chemistry that's behind some of the biggest environmental challenges we face. We're talking about the hidden reactions happening all around us, in the air, in our water, even with our climate. And what's wild is how it connects some things you would never think are related.
I know, right? It sounds like the setup to a really weird joke, but the answer, believe it or not, is chemistry. Each one of these things is at the center of a very specific chemical reaction that has a huge impact on our planet. So let's start connecting those dots.
First up, let's look up at the sky. You know, the atmosphere isn't just this big empty space above us. It's actually a massive chemical reactor. And sometimes the reactions that happen up there are, well, they're not exactly friendly to us.
I'm sure you've seen this before. That kind of gross, brownish haze that just hangs over a big city on a hot, sunny day. That's photochemical smog. And it's not just fog or dust. No. It's the direct result of a chemical transformation that's literally happening right there in the air. So, how does this stuff even form? Well, it all starts inside a car's engine. The intense heat in there cranks out this colorless gas called nitrogen oxide, or NO. That gets shot out the exhaust pipe, and once it hits the open air, it reacts with oxygen. That reaction transforms it into something new, nitrogen dioxide, or NO2, and that is our culprit. That's the reddish-brown gas that gives smog that ugly color and is so tough on our lungs. All right, next up on our little tour of the atmosphere is acid rain. Now, all rain is naturally just a little bit acidic, thanks to the carbon dioxide that's already in the air. But that's not what we're talking about here. We're talking about rain with a pH below 5.6, which is acidic enough to actually eat away at stone buildings and really harm whole ecosystems. So, what's the recipe for this acid rain? Well, the main ingredient is sulfur dioxide, which gets created when we burn fossil fuels like coal. Then you mix that with the nitrogen oxides coming from our cars, and you can even throw in some natural sources like volcanoes. Put it all together, and you've got the perfect chemical storm.
Okay, let's go way up into the atmosphere. Up there, we have this absolutely critical defense system, the ozone layer. The best way to think about it is like Earth's sunscreen. It's this layer of molecules, O3, that absorbs most of the sun's really nasty high-energy ultraviolet radiation, protecting pretty much all life down here on the surface.
But here's the thing, that protective layer is incredibly fragile, and the destructive power of a single, tiny atom against it is just astonishing. A single chlorine atom can kick off a chain reaction that destroys tens of thousands of ozone molecules. To really get a sense of that scale, let's break it down.
Let's start right here. This represents just one single chlorine atom. It gets broken off from these superstable man-made molecules called CFCs, chlorofluorocarbons, that we used to have in everything from spray cans to refrigerators. It seems so harmless, right? I mean, it's just one atom. What could it possibly do?
Well, here's the crucial part. That one little atom acts like a catalyst. It's this unstoppable little wrecking ball setting off a devastating chain reaction. Before it's finally taken out of commission, a single chlorine atom can rip apart up to 100,000 ozone molecules. It's just a staggering example of how a tiny bit of pollution can have a massive impact.
So while some chemicals are up there damaging our atmospheric shield, others are changing the very climate we live in right here at ground level. And that brings us to our next big topic, what's often called the greenhouse effect, or as I like to think of it, Earth's warming blanket.
You know, the greenhouse effect is actually essential for life. Without it, Earth would basically be a frozen rock. Certain gases in the air act like a blanket, trapping some of the heat that reflects off the planet's surface. So the problem isn't the blanket itself. The problem is that our activities are making that blanket thicker and thicker and thicker.
This timeline really tells the story of the main greenhouse gas, carbon dioxide. You can see that before the Industrial Revolution kicked off, CO2 levels were pretty stable, right around 280 parts per million. But once we started burning fossil fuels on a massive scale, that number jumped, and the projections show it just keeps on climbing.
But here's what's really interesting. CO2 isn't the whole story. Not even close. If you look at it molecule for molecule, other gases are way more powerful at trapping heat. Methane, that's CH4, is about 25 times more potent. And then you have nitrous oxide, N2O, which is a mind-boggling 300 times more potent than CO2.
And each of these gases presents its own unique challenge, right?
The CO2 we pump out from burning fossil fuels sticks around in the atmosphere for over 100 years. Methane, a lot of which comes from agriculture and livestock, has a shorter lifespan, but it packs a much bigger short-term punch. And then there's nitrous oxide from industry, which is both super potent and incredibly long-lasting.
All right, let's shift our focus. We've talked a lot about the air, but now let's bring it back down to Earth, literally, to the ground and the water. The chemistry here involves pollutants that don't just float away. Oh no, these guys stick around, and they have a nasty habit of working their way into the food chain.
So there's this key concept called bioaccumulation. Let me paint you a picture using mercury as an example. So, tiny bacteria in the water can convert mercury into a really toxic form. Then, little fish absorb it from the water. Then, a bigger fish comes along and eats a whole bunch of those little fish, accumulating all of their mercury. This just keeps going all the way up the food chain, which means the predators at the very top can end up with dangerously high levels of these toxins in their bodies.
And this problem goes way beyond just mercury. We've created all these synthetic chemicals that the environment just doesn't know how to break down. Things like benzene from gasoline, which is linked to cancer, or PCBs, which can mess with hormones. Even pesticides like DDT. I mean, they were designed to be toxic and persistent. And just like mercury, they build up in the fatty tissues of animals, including us.
Okay, I know that all sounds a bit bleak, but here's the hopeful turn in the story. The same human ingenuity, the same understanding of chemistry that got us into some of these messes is also giving us the tools to fix them.
So let's go back to that car exhaust, that nasty cocktail of toxic gases. The solution is something called a catalytic converter. You can think of it as a little chemical matchmaker inside your car's exhaust system. It uses precious metals like platinum to basically force those harmful pollutants to react with each other and transform into harmless stuff, like carbon dioxide, nitrogen, and plain old water. It's literally chemistry cleaning up after chemistry. It's brilliant.
And what about that acid rain problem from coal plants? Remember, the issue is the massive amount of sulfur dioxide being released. Well, the solution for that is an industrial scrubber. These huge systems force the exhaust gas through this wet mixture of limestone and water. The limestone reacts with the sulfur dioxide and basically captures it, pulling as much as 95% of it out of the exhaust before it can ever reach the atmosphere and form acid rain. So here's the bottom line. Chemistry is an incredibly powerful tool. We saw how it creates the smog in our cities, how CFCs from an old spray can could literally tear a hole in our planet's sunscreen, and how methane from a farm animal helps warm the globe. But we also saw how that same tool gives us solutions, like the catalytic converter. The invisible reactions happening all around us are going to keep happening, but it's our understanding of them that will truly shape the world of tomorrow.